In episode 79, we introduced the general architecture of a CPU, a single core processor. And one of the things that's really important about any processor development is we like to improve performance with every single iteration. Now, this is a very, very old method of implementing performance or increasing performance. In fact, Charles Babbage's Analytical Engine apparently did this to a degree. But what we're going to talk about today is something called pipelining. Now, pipelining is a way of getting improved performance from a processor without increasing the processor's speed. To show how this works, I'm actually going to use the example of a fast food drive-through window, okay? Now, many of you probably have seen this idea of going in your car to get food, right? Now, there are usually, and there are some different ones, different arrangements and so forth. And in fact, if we stick with this theory, there's a lot of processor enhancements, a lot of architectural performance enhancements that we can get out of our CPU that have an analogy when it comes to a fast food drive-through. But let's go ahead and use this just for the idea of pipelining. Now, there's a couple of stages that you have to go through. For example, you have the one window where you place your order, right? And then another window, assuming you don't have some sort of a order ahead or pay before and so forth. And we'll talk a little bit about that also when we start talking about more architectural features. But in an old style drive-through, you've got a window to order, a window to pay, and then a window to pick up, right? Now, let's just assume that each one of these windows, let's just say it takes 1 minute, all right? So we've got 1 minute to order, 1 minute to pay, and 1 minute to pick up. All right. So how long does it take you to get your order? Well, it takes you pretty much 3 minutes, right? On average, we're ideal here. It takes you 3 minutes to go from the beginning to the end here. So as far as the user experience is concerned, it's a 3-minute process. And in fact, usually because you're actually doing some driving between these windows, there's actually some time here, but we'll get to that when we start talking about more advanced architectural features. What we're looking at is a 3-minute process, okay? Now, why on earth do restaurants do this? Why do fast food restaurants do this? I mean, why don't they just have a single window where you order, pay, and pick up? All three, still 3 minutes. Still 3 minutes. And granted, maybe everything's a little bit more crowded inside the restaurant, but I'm sure they'll figure it out. You just do one window for ordering, paying, and pickup. Still 3 minutes, and in fact, you don't have to drive. So it may in fact be a little quicker for you as the customer. Well, the problem is you're not the only customer. If you were the only customer, if you were just going to be the only person to come to that window, then it wouldn't be any improvement. There would be no need for the fast food restaurants to create these stages. However, you're not the only person. And so when you look at the number of customers that they can get through their drive-through, they've actually got a performance improvement here. What happens is it still takes you 3 minutes from the beginning to the end in order to do your pickup, right? In order to do your order. But how fast are customers leaving? Well, if you've got one customer in order, one customer in pay, and one customer in pickup, every minute they're moving forward, right? And that means that one customer is leaving pickup every minute. How much faster is that? Well, as far as the restaurant's concerned, they're able to service customers 3 times faster. Instead of being 3 minutes with one window, they've got 3 windows and one customer is leaving once every minute. All right. Turns out the same is true when it comes to processors. When we talked about the architecture of a processor, we had the bus interface unit. And the bus interface unit, the purpose of the bus interface unit was to grab the next instruction from memory. So it's grabbing instructions from memory. It passes them to an instruction decoder. All right, and the instruction decoder, well, decodes instructions, figures out which circuits need to be energized in order to perform the operation. And then we also had the arithmetic logic unit and the registers that performed the operation. And so it went something like this. You had step 1, fetch the instruction. That's the first step. That's the first stage. That's the first window. Step 2, decode the instruction. All right. Step 3, execute the instruction. Now, this is a big generalization. In fact, executing the instruction may be something like storing or loading. So there are actually a number of things that might encompass the execution of an instruction. But really, the processor has this locked step. I'm going to fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. All right. Now, think about it this way. What did the bus interface unit use in order to fetch an instruction? Well, it used the instruction pointer or the program counter. The instruction pointer or program counter was a register, an address register, which contained the address of the next instruction to fetch. Okay? So as long as that instruction pointer or program counter is pointing to the correct instruction, the bus interface unit can just keep fetching things, right? Well, how did we decide how to modify the instruction pointer? Well, remember that especially for any sort of a processor that uses a fixed length instruction, it just simply added the length of the instruction so that to the instruction pointer so that it knew what next instruction to fetch. In fact, even if the length of our instruction changed from instruction to instruction, a quick check with the instruction decoder should figure out quickly how much to add to the instruction pointer. It adds that to the instruction pointer, and so while we're in the process of decoding, we can go ahead and fetch. Well, once the instruction decoder has decoded it and has energized the circuits to be executing the instruction, the bus interface unit passes along what it fetched just now and passes that along to the instruction decoder, and the instruction decoder updates the instruction pointer so that the bus interface unit can fetch the next instruction. And so what we can do is, much like the drive-through, we can actually be doing a fetch, decode, execute all at the same time. All right, let me go ahead and model this with just kind of a timing diagram to show exactly how this is working. Now, what we are going to talk about here is the idea that if one instruction can be divided into 3 steps, so we've got fetch, decode, and execute. So this is one full instruction. And in fact, I'm just going to go ahead and say instruction 1, right? So we fetch it, we decode it, we execute it. Now, one of the other kind of parameters that we're going to be talking about, in order to execute one of these stages, one of these windows, so to speak, in our fast food drive-through analogy, but one of these stages, it takes 1 cycle. And so what I want to know is how many cycles it takes to execute this instruction. So for a full instruction to execute, it takes 1, 2, 3 cycles, okay? So if I've got, let's just say I've got 5 instructions. I'm probably not going to make it going this way, so I'll just add another instruction here, call this instruction 2. So I've got instruction 1, instruction 2, instruction 3, instruction 4, instruction 5. And so I do the fetch, decode, execute, fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. Now, this diagram here, showing as time is going on, is what it would look like if our processor could only do one of those things at a time. It could only fetch, or it could only decode, or it could only execute, only at one time. So our fast food restaurant only has one window. All right. So this is non-pipelined. How long does it take to execute our instructions here? Well, it takes 1, 2, 3 cycles times 5 instructions, so it becomes the duration becomes 5 times the number of, so 5 instructions times the number of stages, 3. It takes 15 cycles. All right, 15 cycles. Can we improve upon that with pipelining? Well, let's take a look. Our diagram in a pipelined architecture looks a little different. Now, what we're going to do is for instruction 1, we're going to fetch it. Instruction, the bus interface unit, its job is just to go ahead and use the instruction pointer in order to fetch the next instruction to execute. As soon as it finishes fetching it, it passes it along to the instruction decoder. But the instruction decoder has already incremented the program counter or instruction pointer so that the bus interface unit can fetch the next instruction. So this is I2. Now I2 is being fetched while I1 is being decoded. Now once the decode is complete, the instruction decoder passes along the information to the ALU and to the registers in order to execute this instruction. By then, the bus interface unit has finished fetching the instruction, so it passes it along, the fetched instruction along to the decode unit, and the instruction decoder says, by the way, here's the instruction pointer pointing to instruction 3. And you get this lockstep of the one instruction is being executed while the next instruction is being decoded, while the next instruction is being fetched. And so if we look now at the execution of 5 instructions, so there's I1, I2, I3, I4, I5, how long does it take now? Well, it takes 1, 2 stages to start filling up the pipeline, to start filling up all of the resources in our CPU. So it takes 2 cycles, but then once those 2 cycles happen, we are executing an instruction once every cycle. So I've got 5 instructions here. So what I have is 2 cycles to fill the pipe. And then 1, 2, 3, 4, 5 cycles to execute them. What I've got is 7 cycles. An improvement? I should say so, and better than 50%. Now, what's interesting here, and I'm going to do a little bit of math, in fact, calculus. You may have seen this idea of a limit, right? A limit. And what I'm looking at is if I have n instructions, all right? As the number of instructions I execute goes up to infinity, what is our ratio? What is our speed up? Well, what I want to do is I want to do the limit as the number of instructions I'm executing goes to infinity for the non-pipelined version divided by the pipelined version. And that'll tell me what the speed up is. Well, what is the expression for my non-pipeline version? It's the number of instructions times the number of stages per instruction. So this becomes 3n. All right. What is the expression for the pipelined version? Well, the expression for the pipeline version is 2 cycles to fill the pipe, but then 1 cycle for each of the instructions for execution. So I've got 2 plus n. All right. Now, looking at what happens when you look at these limits is you say, okay, as n starts getting bigger and bigger and bigger, some parts of this expression are going to become inconsequential. They're going to kind of fade away, drop out. What happens is n gets really big. So for example, what if n is equal to 1,000? This would be 3,000 over 1,002. That 2 is starting to look not really important. What about if n is equal to 1,000,000? 3 million divided by 1,000,000 and 2. So the 2 got even smaller. So this 2 actually goes away, and the limit as the number of instructions goes to infinity of this expression is just 3n over n. Our n's cancel out, and we get 3. So, as the number of instructions we execute gets bigger and bigger and bigger and bigger, this speed up from going from a non-pipelined architecture to a pipelined architecture, the speed up becomes close to 3. Now, let's go back to our fast food analogy. Our fast food analogy says if I've got 3 windows, I can go from 3 minutes per customer to 1 minute per customer, okay? What if I could make this into 6 windows? Maybe you have one window where you order your food, and then another window where you order your drinks and, you know, ketchup and things like that. And then one window where you pay, and another window where you get your change, and then another window where you receive your food, and another window where you receive your drinks. Okay, so we've made it into 6 windows. Now, it's still a 3-minute process. How long is each one of those windows? Well, now each one of those windows is 30 seconds. And how fast, if all of those windows are filled up, how fast are we getting customers out of our drive-thru? 1 every 30 seconds. How much faster is that? It's 6 times faster. So if I were able to figure out how to divide each one of these stages in half, our cycle would get smaller. So if I've got fetch in 2 stages, our cycle would be half of what it was with the 3 stages, and then I could actually experience a speed up of 6, because what would happen is my cycle would be smaller, still takes the same amount of time to execute an instruction, but now I'm doing it in 6 stages. The 6 stages say that my cycles are now smaller, they're faster. How much faster? What's our speed up now? Well, our speed up would be, if for non-pipelined, it'd be the number of instructions times 6 to give you the number of cycles. What about pipelined? Well, it would take 5 cycles to fill up the pipe, but then 1 cycle per instruction after that. And our speed up would end up being 6n divided by 5 plus n, which would reduce to 6 as the number of instructions went to infinity. Now, there's a problem. What's the problem? Well, the problem is branches, specifically conditional branches, and I'll tell you why. What was it that this whole process depended on us what? Knowing where the next instruction to execute was. Making sure that the instruction pointer, or the program counter, was pointing to the correct address. Well, we sometimes don't know what the correct address is until we get to it, until we've executed it. So for example, if I've got a for loop, some sort of a for loop, this right down here is actually going to, for the most part, or a while, let's say a while loop. I know my syntax looks a little funny here, but this last instruction right here, I will keep branching up here until I'm done with the loop, right? How do I know if I'm supposed to branch up here? Well, I won't know that I'm supposed to branch up here until I've executed the last instruction of this loop. And the last instruction of this loop, which is typically a compare, check to see if I can branch back up to the top. If I am branching back up, guess what? I have to flush my pipeline. And that's what the term is called. It's called flushing the pipeline. And so what I do when I flush the pipeline is I get rid of everything that I've already decoded, because I realize that, for example, let's say that this instruction 3, when I execute that, I realize that I had fetched the wrong instruction. So what I have to do is I have to get rid of everything I fetched, because it doesn't need to be executed. It's wrong. And I need to fetch then what I was supposed to fetch because of the loop. So conditional branches, in fact, jumps to functions, things like that. Anything that is not predictable, not a good way for us to predict where the instruction pointer is going to be without executing, will flush the pipe, and that reduces performance. In fact, for that reason, some compilers will do what's called unrolling a loop in order to improve performance. And what they'll do is, let's say that I have to do this loop 5 times. So instead of doing the loop looping 5 times, they'll just make 5 copies of the loop so that I don't have to do any branches. That will improve performance and help support our pipelined architecture.